With those nails, we could count them. It's possible. With atoms, we cannot count them. It's impossible, and so we have to use their mass to count them. This is kind of interesting. Even if you could see atoms, and you counted them 24 hours a day as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. Think about it. Spend the rest of your life, no sleeping, no anything, just counting for the rest of your life. You could maybe count as many atoms as are in a grain of sand. We're dealing with some really, really big numbers here. Dozen is a great unit. A dozen is how many? 12. Dozen is great for donuts and bagels and things like that. Eggs, right? It's way too small to be useful for atoms. Can you think of another unit that is a counting unit that's a bigger number? You get a package of paper for your computer. A ream. A ream is 500 sheets of paper. So that's getting better. That's 500. It's still way too small. Another unit like that is a gross. Ew, gross, right? No, it's actually a unit. Gross is 144. It's a dozen. It's 1 dozen. It makes me think of double. It makes me want to go to In-N-Out. But these are just counting units. Well, chemists have their own counting unit, and it's called the mole. M-O-L-E. It has the abbreviation MOL, which I personally think is dumb, because isn't that short enough already to just drop the E? Why even bother? But anyway, if you see MOL, that's mole. 1 mole is a really big number of things. 6.022 times 10 to the 23rd. That's a mind-bogglingly large number. That's a 6 with 23 zeros after it. Okay? And that's what we call the chemist's dozen. And this is not mole, a sauce, and it is not a small, furry, nearsighted animal that makes holes in your and lumps in your grass. It's mole. And I'm not exactly sure where they came up with the name, but it's there and it seems to have stuck. So there we are. So just like a dozen of anything is 12 of that thing, 1 mole of anything is just this other number of things. So mole can be a confusing idea for beginning chemists. But think of it as being like a dozen. It's just a particular number of things. It's just that the number's really weird. It's 6.022 times 10 to the 23rd. That's called Avogadro's number. It's named after this guy, Amadeo Avogadro, who did some really amazing work and helped us to figure out some things that led to the mole. And so we named this number after him. So a mole of marbles, 6.022 times 10 to the 23rd marbles. A mole of sand grains, 6.022 times 10 to the 23rd sand grains. I think a mole of marbles, I really need to write these things down and get them into the PowerPoints. I think that would cover the surface of the earth to a depth of about a mile, if you had that many marbles. Think about that. That's a lot of marbles. Oh, I have to tell you one other thing about this number. It's just a little personal thing about the number. So, chemists celebrate Mole Day, right? 1023. 1023 is October 23rd. We actually have class, I think, on Mole Day, which is going to be fun. I'm not sure what we're going to do, but I don't know. We'll do something. So that's Mole Day. So this is just kind of fun. My husband is a chemist, and I'm a chemist, and our 4th child was born on Mole Day. And my husband just thought that was the coolest thing ever. It would have been even more cool if we could have had him at 6:02 a.m. That would have been the best thing. We didn't even hit 6:02 p.m. I think it was like 8:30. But at that point, you really just don't care at all. He still made it on Mole Day. And what was even more amazing is he weighed 10 pounds, and he was 23 and a half inches long. So we got two 1023s out of him. He was a moose. The nurses were bringing their other nurse friends to see this giant baby. It was really pretty funny. But so he's our mole baby. And we actually did have a very brief conversation about giving him the middle name Avogadro, but we wisely decided against that. So he has a Japanese middle name like his brothers and sister. So 1 mole of atoms, ions, or molecules is going to be a reasonable size of atoms, molecules, or ions. So here in this picture we have 22 real copper pennies. Those are the ones made before 1982 that are actually copper all the way through. That represents about 1 mole of copper atoms. So this is an amount of atoms that you can deal with. A reasonable amount of stuff is a mole. So 2 helium balloons, a mole of helium atoms. So atoms are crazy small, their masses are crazy small, but by talking about a mole of them, we get them up to quantities that we can see and actually deal with. And so the mole is just a really useful unit. The number 6.022 is not an exact number. That has been measured. It's actually known to more digits than that, but we don't really need to know them for this level of chemistry. But the numerical value is defined as being equal to the number of carbon atoms, the number of atoms in exactly 12 grams of pure carbon-12. And because of the way the mole is defined and the way the atomic mass unit is defined, we end up with a really neat relationship. We get this relationship between the mass in grams and the number of atoms. And I know I'm just going to jump ahead of myself, so I'm trying not to. So this relationship allows us to count atoms by weighing them. Come on, there's got to be... Oh, it's got to be coming. I'll just be patient. I'll just be patient and wait. So let's do this one. Convert 7.2 moles of neon to the number of neon atoms. And here I'm giving you what a mole is because I just told you about this, so you probably haven't memorized that just yet. That is a number you need to know. 7.2 moles. These come down to being unit conversion problems or dimensional analysis problems. I have moles and I want atoms. So I'm going to multiply by number of atoms. Oh, that's just not going to fit at all. I'm going to multiply by number of atoms and I'm going to divide by moles, just so the units work out. And here's my relationship. 1 mole equals Avogadro's number of atoms, just like 1 dozen equals 12 things. Okay? So it's 1 mole and 6.022 times 10 to the 23rd atoms on the top. And this number here is one of the main reasons that we need to learn how to use scientific notation on our calculators, because there is no other way to get this number into your calculator. Your calculator can usually only handle about 9 digits, and after that it's just done. So we need scientific notation. So if you have your calculator with you, pull it out. Let's make sure we remember how to do this. So 7.2 times, and I'll write this down here. This is what you're going to punch on your calculator. 7 and the 0.2 and then the times button. And then you're going to do 6.022, and all of that is awesome and great. And then people lose their brains. Now you do the EE button, or it may be an EXP button. They do exactly the same thing, and some people have a times 10 to the x button. Not 10 to the x, but times 10 to the x. This one is less common. Either of these buttons does times 10 to the, and then you put in the 23. And then you press the equals. You never do times 10 and then EE. That's going to get you the wrong answer. So 7.2 times 6.022. EE23 equals. And then the calculator, depending on which one you have, my calculator is showing me this. 433,584, and then it's got a little 24 up here. This is calculator language. We don't write calculator language down when we're communicating with people. We need to convert this into human math language. Okay? That means there's a times 10 to the in there. And I'm going to think about my significant figures, and I started with 2, so I'm going to end with 2. And I'm going to have 4.3 times 10 to the 24th atoms. And there's my answer. Does anyone need me to speak to their calculator? It's never your problem. It's your calculator's fault. Okay, and I am the calculator whisperer, and I can make your calculator behave by magic. Anybody need me to speak to their calculator? Y'all got the right answer? Not getting any feedback from you guys. Wake up. You're yawning. You're going to get me started. Okay, let's do another one. 5.2 times 10 to the 25th platinum atoms. How many moles is that? Think, how many dozen is that? If you have a hard time remembering what to do, think, well, how would I do this with dozen? Because you're familiar with dozen, you can do that. And then swap 12, put in Avogadro's number, and instead of dozen, put in mole. And that can really help if you're losing your way. 5.2 times 10 to the 25th platinum atoms. So we're trying to get to moles. So this time we multiply by mole and divide by number of atoms. We don't have to remember any formulas or anything because the units tell us what to do. The units are saying multiply by moles, divide by number of atoms. And then this relationship between moles and atoms is 1 mole is Avogadro's number, 6.022 times 10 to the 23rd, Michael's birthday, atoms. We don't want to put that on the top because that would be like saying that 1 egg is 12 dozen eggs. And that doesn't make any sense, does it? 12 dozen eggs is 144 eggs. That's way more than 1 egg. So it's always 1 mole and Avogadro's number of atoms. And this is where it'll really show up if you're doing it wrong on your calculator. So 5.2 EE 25. You can multiply by 1 if you like, or you can skip that because it won't make any difference. Divide by 6.022 EE 23 equals. And this should also have 2 significant figures, 86 moles. Are your calculators behaving? Any questions? Okay, before we talk about this slide, I want someone to tell me what is wrong with this picture. There's only 11 of the small nails. Seriously? The point of this is that there's a dozen, and there's only 11. And what's worse, is I notice that. Why do I see these things? Why do I count the nails? And then the other question is, why does it bother me so much? Okay. There, 12 nails. Okay, now we can go on. So here we have a dozen large nails and a dozen small nails. Are they going to weigh the same? No, because each large nail weighs more than the small nail. So a dozen large nails is going to weigh more than a dozen small nails. The same thing is true for atoms. If you have a mole of big, heavy atoms or a mole of small, light atoms, they're not going to have the same mass, are they? So the weight of 1 mole of atoms is going to change for different elements. Here's a picture of 1 mole of sulfur. That weighs 32 grams. And here's 1 mole of carbon. You can see that's less, isn't it? Because each atom is smaller. And 1 mole of carbon weighs 12 grams. Same number of atoms in these two samples. But because the atoms are different sizes, the samples are going to be different sizes. Which brings us to molar mass. So the atomic mass unit was defined as 1/12 the mass of a carbon-12 atom. And so a carbon-12 atom then had a mass of 12. They picked carbon-12 because it's stable, it's plentiful, it's easy to get to, it's easy to work with, it's just convenient. So carbon-12, 1/12. The molar mass of any element is the mass of 1 mole of atoms of that element. And because of the definition of the mole being equal to the number of atoms in a 12-gram sample of carbon-12, the molar mass in grams is numerically equal to the atomic mass in atomic mass units. Now that may have just sounded like a whole bunch of words. So 1 copper atom, just 1 atom, weighs 63.55 atomic mass units. And this name is pretty descriptive. Atomic mass unit. This is a unit for determining the mass of an atom. I mean, how much clearer can you get? So 1 atom weighs that many atomic mass units. A mole, a chemist dozen, this huge number of copper atoms, has a mass of 63.55 grams. The number is the same. You see that? 1 atom is that many atomic mass units. A mole of them is that many grams. So on the periodic table, under each of the element symbols is the average atomic mass of that element. And so it serves 2 purposes. It tells us the average mass of an atom in atomic mass units, or the average mass of 1 mole of atoms in grams. And so that gives us a really great relationship that we call molar mass, the mass of a mole. Yes?
Does that correlation apply with most of the elements?
All of them. And it's because of how the atomic mass unit and the mole were defined. It was done intentionally. It wasn't just a happy accident. It was done intentionally that way. So we look at copper on the periodic table and we see the number 63.55 under it. And that gives us the molar mass. It's that many grams per mole. Atomic mass, mass of an atom. Molar mass, mass of 1 mole of atoms. Well, that molar mass is going to be different for different elements. A mole of sulfur is going to weigh 32.07 grams. But it's still Avogadro's number of atoms. 12.01 grams of carbon is 1 mole. Still the same number of atoms. 1 mole is always Avogadro's number of atoms. But the mass changes. Just like a dozen nails is always 12 nails. But the mass of the dozen nails is going to be different depending on whether they're big nails or small nails. So the lighter the atom, the less mass in 1 mole of that atom. And the molar mass is a conversion factor that we will use the rest of the semester to convert between grams and moles. Chemists care a lot about numbers of atoms because particles react, elements combine in particular ratios of number of atoms. And so that's really more important than mass. But mass is useful because that's something we can measure. We can't count the atoms, but we can weigh them and use that to help us decide how many there are. So let's look at converting between grams and moles. So calculate the number of moles of calcium in 91.4 grams of calcium. Dimensional analysis. There is one number here. Let me get my chalk color back here. 91.4 grams of calcium, and they want the number of moles. So we're going from grams to moles. That's the molar mass. That's on the periodic table. So we go to the periodic table and we find calcium, and under calcium, 40.08. So that means that 1 mole of calcium atoms weighs 40.08 grams. That is a conversion factor. Grams to moles, we just set it up for dimensional analysis, 91.4 grams of calcium. Grams to moles, we're multiplying by moles and we're dividing by grams. So the units work out. We look at this relationship. 1 mole, 40.08 grams. 1 mole, 40.08 grams. So we get 91.4 divided by 40.08. My calculator shows me a big long mess, but I'm going to look at my sig figs. This is 3 significant figures, and this is 4. And so I'm going to round my answer to 3 significant figures. It's going to be 2.28. And the unit that's left is moles of calcium. Any questions? This is like one of the most important kinds of calculations in all of chemistry. Use it all the time. We can go from moles to grams. Calculate the mass of aluminum in grams in 6.73 moles. So this time we're starting with moles, and we're going to grams. The conversion factor comes from the periodic table. 1 mole of aluminum, we find aluminum 26.98 equals 26.98 grams. And then we let the units tell us what to do. 6.73 moles, we're going to multiply by grams and divide by moles. So the units cancel out. There's no remembering, do I multiply or do I divide? Put the units in and they'll tell you what to do. 1 mole is 26.98 grams. So we've got 6.73 times 26.98 equals, how many significant figures should this answer have? 3. What we're starting with has 3. And we'll see this a lot, that even using a periodic table where the numbers are rounded to 4 significant figures, that will not usually limit our answer. Usually they use 3. So we'll come up with 182 grams. So if you are super significant figure phobic, and that was just horrendous torture for you and it didn't make any sense, just using 3 digits in your answer is usually going to work. It's kind of a little sig fig hack. Most of these are going to start, whatever you start with is what you'll end up with, and a lot of times in these problems it's 3. Any questions? We can also convert between grams and numbers of atoms. How many aluminum atoms in an aluminum can with a mass of 16.2 grams? Well, here's our number, 16.2 grams. This time we're not finding moles, we're finding atoms. How many atoms? Well, do we know a relationship between grams and atoms? Well, let's write down what we do know, okay? We know that 1 mole of aluminum is 26.98 grams. That's from the periodic table. How many atoms is that? 6.022 times 10 to the 23rd. Because 1 mole is always 6.02 times 10 to the 23rd. That's always true. This number is specific to aluminum. 1 mole of aluminum is 26.98 grams. We could do this in 2 steps. We could go from grams to moles and then from moles to number of atoms. But we don't really need to, do we? Because here we have a relationship between grams and atoms. So why do 2 steps if we can do 1? So we can go directly, that's the wrong place, over here. So grams, 16.2 grams. And then just following our path for dimensional analysis, grams to atoms, we're going to put atoms on top. And we're going to put grams on the bottom. The units, just to put them in the right place so they cancel out. If you still haven't seen the light, if this hasn't become clear with the whole dimensional analysis thing, today would be a good time to ask me some questions about that and figure it out. Because it's not going to go away. There's a lot of it in this chapter. And once you figure it out, it's so much easier. It'll just really make your life easier. So now we look here, and 26.98 goes with grams. We have to keep the number and its unit together. We can't switch partners here. And 6.022 times 10 to the 23rd atoms. Now we have some math to do. 16.2 times 6.022 EE 23 divided by 26.98 equals, how many sig figs should this answer have? 3. So 3.6, and that's going to round up to 2, 3.62 times 10 to the 23rd atoms. That's a really big number. Is that reasonable? An aluminum can. That's something that you can see, right? Hold in your hand. Anything that's visible is going to have a large number of atoms in it. So we're expecting a big number like this. What if I did my math wrong and came up with something times 10 to the minus 23rd atoms? Would that be reasonable? No. Would that even be possible? That would be less than 1. You can't even have half an atom. Hiroshima. If you have half of an atom, it's not an atom anymore. It's a collection of strange particles. And so if you're ever calculating number of atoms and you come up with less than 1, check your work, you did something wrong. That's like, trying to calculate the number of people in Fresno County and coming up with 0.27. Right? Is that possible? No, it's ridiculous. Something went wrong with the math. And that's where it really helps to look at your answer and ask yourself, is that at all reasonable? And sometimes you can save yourself some points that way. Any questions about this problem?